Okay, great. Thanks for your patience, everybody. So again, just really excited to be supporting this challenge with support from Google.org and to be partnering again with Zindi. I'm Jennifer Pratt Miles. In addition to my work on Lacuna Fund, I'm a partner with a not-for-profit organization called Meridian Institute. And Meridian serves as an incubator for Lacuna Fund, providing secretariat services, collaboration and facilitation, as well as fiscal sponsor services. And at Meridian, our mission is to help people solve complex and controversial problems, make informed decisions, and implement solutions all through collaboration. So, as many of you know, a lacuna is a gap or a missing portion of a manuscript or piece of music. And the name represents Lacuna Fund's mission to help fill those gaps in the data sets that are used to train and evaluate machine learning models. Um, and I would like to share the next couple slides with you. So I'm going to try one more time. Well, I'll just share that um, that Lacuna Fund is a coalition of funders, data scientists, and researchers from around the world. And are the funders that make Lacuna Fund possible range from public sector agencies to private philanthropies that are all committed to a mission of machine learning that is more representative and therefore more accurate and less biased, and that serves the world more equitably. And as I mentioned, I want to really thank Google.org for sponsoring this challenge and some of the other partners, including the Rockefeller Foundation, Canada's International Development Research Center, Germany's Fair Forward Artificial Intelligence for All program, and Wellcome Trust, all of which contributed to the um, the, the the pool of funds that is supporting the malaria detection data set that we'll be talking about today. We have an amazing global multi-stakeholder steering committee that I'd love for you to be aware of. So I'll put a link to it in the chat. And they bring a balance of perspectives from funders as well as data scientists, innovators, those working on data governance and ethics, and as well as those with a technical background and perspective. So they're an amazing group that provide guidance for the fund. And in terms of filling the data gap, I'm really excited to share with you that Lacuna Fund has made over $8 million in grants to date, funding 58 data sets globally. 42 of those teams and data sets are based in Africa. And to date, 26 data sets have been completed in a range of areas, including agriculture, health, and languages. So we're really excited to start seeing the impact. And we are also really supportive of ensuring that the data sets created with funding from Lacuna Fund are shared and reused. And to that end, we've provided a set of guidelines on dataset documentation and hosting, which are available on the Lacuna Fund website. You can find links to the completed data sets on the Lacuna Fund website as well. They're hosted in lots of different places, but we provide a central place where you can find links to them. And then we also try to share information about the data sets once they become available via our newsletter and social media, and by supporting teams to present their data sets at conferences and events, and through challenges like this one. So once again, really excited to be partnering with Zindi, Makerere University, and Google.org for this challenge. And if you have any questions, you can contact us through the Secretariat email, which I'll put in the chat. So thanks very much, and back over to you, Paul.
So much, Jennifer. Oh, thank you so much, and sorry for the issues with the slides, but I think the message came across loud and clear. You're also most welcome to share your slides with me, and I can make sure all the attendees get them. If you can, as you say, if you can pop a contact email address into the chat, that would be really valuable to everybody as well. I think maybe I will ask Darius to take us through the starter notebook. Meanwhile, um, and hopefully Rose will be able to join us, but I don't want to sit here quietly waiting for that. Darius, are you ready to go ahead?
Yes, Paul, I'm
Okay.
ready.
All right.
Yeah,
Maybe you can just touch briefly on the nature of the challenge before you go ahead, and then we can have Rose uh, speak when you're done and when she joins. Over to you.
sure. Let me share my screen.
You can go
So,
ahead.
yeah, so guys, welcome. I'm going to take you through this challenge. I think first we can go through what the challenge is, what's expected of you, uh, what evaluation you are going to use, all that. And then later, maybe you can go through the starter notebook. So for this challenge, we have 2 months left for you to come up with the good models. So the challenge itself is about building a detection model. So it's a multi-class object detection and classification model to classify malaria parasites in blood slides. So you can go through the description. It's on the Zindi website. I hope everyone has already registered and made a submission. If you have not, later I'll show you through the starter notebook on how you can do that. So this is the challenge itself. The evaluation metric for this challenge is the mean average precision intersection of a union with a threshold of 0.5. If you don't know what that is, it means that you are trying to use deep learning or machine learning models to try and predict where the white blood cells is by predicting the bounding box. So it's usually like a rectangle or a square. And then we compare your prediction with what we have. And then we calculate the percentage where there's a union, where they overlap. That's the evaluation metric. And then when you're creating your submission file, this is how it should look like. For each image ID that you are provided with, you're supposed to predict a class. It can be a white blood cell or another. And then you're also supposed to provide a confidence score, like how confident is your model in predicting that this bounding box or these are white blood cell. And then so you have to provide the bounding box coordinates, being the Y mean, X mean, Y max, and X max. Note that for this competition, because we want it to be as efficient as possible, there are some restrictions on the hardware that you can use. So we have restricted this to using an A140 GB Max. That's the A100 GPU by NVIDIA. You can train your model for around 20 hours, but for inference, it has to be 2 hours. For the prices, I think all of us can see it here that the first place is $2,500, second $1,500, third 1,000. And if you don't make it into the top three, I think just by building a model or by committing yourself to this challenge, at the end of the day, even if you don't get a prize, I think you'd have learned a lot on how to build models. Okay, and the challenge will close on November 17th. So that's the brief overview of the challenge. I think, Paul, maybe then next I can move into the starter notebook. We can just finalize on this on the Zindi website on what's there. We want to download the data. This is the data button. For you to access the images, we have provided a G drive. So it's easier for you to download the images and start building a model. Also, we have provided you with a train file, a test file, a sample submission, and also a starter notebook, which I'll go through in just a moment. If you have any queries on this challenge, feel free to post a discussion post on Zindi. We are here to help you in case you have any questions or any clarification or whether you're stuck. Also, when you post, other data scientists across the world can help you. And then after you make a submission, there's a leaderboard where you get to see where your model ranks. So at the moment, Team Epoch, I think are number one with a map of 0.91. If you want to create a team, we want to come together like 4 people, you can create a team and then compete. And also you can view your submissions on this tab. I think I can now move on to the starter notebook unless there are any questions. Paul, should we take questions now or after the...
I think let's complete the presentation and then we can address questions.
So I've prepared a starter notebook. I'm using Google Colab with a GPU, which is A140 GB. This is what's recommended. You can use either this or another GPU that is less powerful than this one. For the starter notebook, I decided to use pre-trained models. I think if you have done like a detection kind of challenge, usually the go-to model is YOLO. You only look once. There are other models out there that you can use, but for this starter notebook, we will be using the YOLO model, which is gotten from the Ultralytics. So the first thing obvious for a data scientist is to import your libraries. In this case, there are some libraries that we can use for data manipulation like pandas, path and shuttle for creating paths and moving directories and all that. Matplotlib for visualization, and then YOLO, the YOLO that we'll be using. So on the Zindi website, we saw that the data or the images are provided in a G drive. You can create a shortcut to your own G drive, or you can download them to your own PC if you have a local GPU, or you can just, if they are in your G drive, you can easily access them from Colab. So the files you are provided with are the train file, test file, and sample submission file, and also the images. So the train contains the image, the class that you are supposed to predict, and the bounding boxes. The test, on the other hand, it just has the image IDs without the bounding boxes and the class. So the test gives you an image, pass that image through your model that you have built, make a prediction, get the bounding boxes, and then create a CSV and upload that CSV to Zindi for scoring. So when it comes to the YOLO model, there are some prerequisites that you have to do, like it has some recommendations on how to build a YOLO model. So the first thing usually is you have to create different directories for different data sets. So usually we have a training data set, a test data set, and also a validation data set. I can try to explain what those are. The train is what you use to train the model. Validation is the data set that you use to evaluate how good your model is. And the test set is what you make predictions on. For the test set, usually you don't have the labels. So that's what this cell does here. The images are provided as a zip file, so we unzip them, and then we load the files. So if we preview the train file, this is how it looks like. We have the image ID, the class, the confidence, and then the boundary box coordinates, and the path to the image. We know that in machine learning, usually you have to change your data into numerical format because computers don't understand strings. So that's why I've mapped the class from a string to an integer. So that's called label encoding. So the class here, because these are training file, the confidence is always 1. But when you make predictions, your model can be 0.9 or 90% confidence, 50% confidence. So take note of that. Also, to increase the performance of your models, we have included a bunch of negative images. So by negative images, we mean that they do not have trophocyte class or white blood cells. So your model should be robust enough that when it's given an image, it can be confident that in this image, there's no trophocyte or there's no white blood cells. So that's what a negative image means. When you want to include negative images in YOLO, usually there's a format that you are supposed to label them or set up the directories. It's recommended that for negative images, you leave them empty. I've provided a link here. If you want to do a bit on more research on how it's done, you can go take a look. But because this is a starter notebook, I think I'll not dive deeper into it. But I'm sure that if you use negative images in building your models, most definitely the performance will improve. So that's a tip for you if you have not used negative images in building models. Maybe even include the negative images, you can have like a spike in the leaderboard and maybe even win this challenge. So usually it's good practice when you're building models to split your data into training and test. Remember that the test data that you are provided doesn't have labels. So for you to gauge how good your model performs locally before you submit your submission to Zindi for scoring, you can split the training data set into training and validation. So that's what I've done here. A suggestion I will make, usually when I started machine learning before, usually I could just split the data set without taking into consideration that an image can contain more than one boundary box. So to avoid data leakage, you should split the the data set if you want to create a validation set based on the image itself and not the bounding boxes. So that's why I dropped the duplicates here. So in this case, I wanted to retain like 75% to train the model locally, and then use 25% of the images to validate the model and see how it performs. Also, it's a good thing to make sure that when splitting the data, you maintain the class imbalance if there is. In this case, there is. So we can see that the trophocyte is almost 70% compared to the white blood cells. There's a 70 to 30 ratio. So you want to maintain this between the training dataset and the validation datasets. So that's what I did there. And then we have to create the directories that we created up there. If you remember, these directories here. So you have to create where the training images will be, the validation images and the test images. And then you have to do the same for the labels. So that's step here. And then after creating the directories, now you move the images from the zip file. Remember, we unzipped the images to, I don't know, we unzipped the images, but now you move the images to their respective directories. So if the image is supposed to be in the train dataset, you move it to the train directory. If it's a validation image, you move to the validation directory, same for test. So the data that we provided you with, it has, I think, X mean and Y mean, they're Pascal annotations. But for YOLO, you have to convert those bounding boxes to YOLO, which usually uses X center, Y center, and width and height. So you have to do that. That's what I did here. YOLO recommends also that you create a YAML file that points to the location where the training dataset is, the validation, and the test. So the YAML file contains, like, for the training dataset, it's in this directory. The validation dataset is in this directory. The test is there. And then we have the number of classes. NC means number of classes is 2, which means we have trophocyte and white blood cells. Another thing you can do before moving on to build a model is doing a quick visualization and see whether the conversion of the bounding boxes from Pascal to YOLO worked without any issues. So if you do a visualization, you can see, like in this image, it seems the bounding boxes were correctly transformed, so they're accurate. Class 0 and class 1. Yeah. So this is what you're supposed to make your predictions on. So on to the most exciting part, which is the modeling part. So you initialize the YOLO model. There are different versions of YOLO. I think they start from YOLO version 5 up to now we have version 9. I used version 8, but you can also use version 9, which is the latest. They have different sizes. I think there's the nano, small, medium. I don't know whether it's large, but you can do a bit of research and see. When you are choosing the model, just consider how long the model takes to train and how long also the inference takes. Because even if you are ranked position 1 in the leaderboard, but your model takes like more than 20 hours, I don't think you'll get the prize. So make sure for training, you use a GPU, which is A100, 40 GB and less. And it takes 20 hours for training and 2 hours for inference. Don't forget that. So in the modeling part, we're initializing the model for training. You have to provide the YAML file that we created up there that points where the points the directories of each of the datasets. That's the training, validation, and test. Also, you have to specify the number of epochs that you're going to train your model on, image size. You can change this. So this is where you have to do like thorough exploratory data analysis. You have to check the images like the width, the height, majority of the images, where do they lie? And then using that information, you can feed it here. In this case, I just used 2048. You can experiment with a larger size or a smaller size, or you can even use progressive training. I don't know whether that's available in YOLO, but you can also check faster CNN or a single shot SSD detection and see whether you can apply progressive resizing when training detection models. I think that's a tip I can provide for you. It has worked before in other competitions and in other challenges. If you include it here, maybe it will give you some performance. So also take into consideration that if you increase the image size, the training time might go up. So you have to gauge on what you want most. There's a thing in data science we call there's no free lunch, which means that if you are gaining something here, you are losing something on the other hand. So if you increase the image size, your model will be more accurate, but then on the other hand, it will take more time for training. So yeah. Batch size the same because we're using A140 GB. Also, batch size takes into consideration the image size. So take that into consideration. Device, we recommend that you just use one GPU. So if you have like a machine, a local machine, a PC that has more than one GPU, we suggest that you just use one GPU for training. And then patience, in this case, it means that how long your model will be patient before stopping training if there is no increase in performance. Let's say your model has the epochs you want to train the model is 30 epochs, but then after 10 epochs, the performance of the evaluation metric doesn't improve. After 5 more epochs, the model will stop. I think this to reduce the consumption of more resources and also to avoid overfitting. Yeah. So when you initialize this model, this is what you get. It downloads the model from the YOLO servers. It initializes TensorBoard in the background if you want to see some images and their labels on how they score. The metrics are improving. You can check that. So it's using automatic mixed precision. This is when during training, the model can switch from float 32 to float 16 data types. This helps the model to train faster, and also in some cases, it can use less memory. That's less VRAM of the GPU. So the good thing about YOLO, before even training starts, it scans the training. It scans the directories that we shared. Remember, we shared here a data YAML that pointed to the directories. Yeah. So it scans to make sure that each image has a label and that there are no corrupt images. Generally, when you're working with images in deep learning, it's recommended to augment your data. That's like increasing the diversity of the images you have. So this is something also you can experiment with and see which augmentations work best. Some of them are here. You can see that there's a blur, there's median blur. There's the, I don't know what this means. I think this histogram equalization. So this is where your creativity will come in, whereby just looking at these images, you could think like, what can I do to this image to increase the probability of a model making a good prediction? Will a flip help? Will increasing the brightness help, or the contrast, or changing this image to gray? Yeah, those are some things you can do. Also, augmentation helps with the reducing overfitting. If you want to go further, there's other methods you can use. I don't know whether Yellow supports like something like mix up or cut mix, but I'm sure faster CNN maybe does. So you could check that out. I think Yellow also supports that. So a bit of research here and there, and you have improved your model. So you can go through this. It initializes the optimizer in this case. It's using I think it's using Adam, or yeah, Adam with the learning rate of this, a weight decay. So with the weight decay also helps in reducing overfitting. If you see that your model performs well on the training data set, but then when you upload your submission file to Zindi, you get that the performance is not all that, then it means your models were fitting on the training data set. So what you can do is add more regularization. Weight decay can help. Also dropout, I don't know where you can put that, but it can also help. So after training the model for about 30 epochs, when usually by default, YOLO saves the best model. So you can load the best model or the best checkpoint, and then you can do an evaluation and see how it works locally. After that, you can point the model to the test data, the test directory, where you have to make the predictions, get the bounding boxes for each image, and then prepare pandas data frame, which you can save as CSV, as a CSV, and then you will use that CSV to upload it to Zindi for scoring. After that, after running this notebook, I think you should get a score of 0.43. Because this is a starter notebook, I think the score is a bit low. I did not do any more hyperparameter tuning or use all those fancy things like a cut mix, dropout to reduce overfitting. But if you do all those things, I think you can improve your score. Yeah, I think that's it. We can move on to the questions if there are any. Paul?
Great. Thank you so much, Darius. I saw one or two questions. I do want to give Rose a chance to address the call, but let's quickly go through questions I can see in the chat. The first is, can we use pre-trained models? I think that you've already answered that.
Yes. Yes, we can. It's recommended to use pre-trained models because I don't think with the 20 hours you can train your own model from scratch. But if you're able to, you are welcome to try that out.
Okay, that's great. So you would in fact recommend pre-trained models. Okay, so the next question is, can we use any model or package?
Yes, you can, so long as they're open source and they're not preparatory, like you don't have to pay to use the
Mm,
model. Yeah,
mhm.
so long as it's accessible to everyone, you can use it.
Thank you. The next question is in the resources section, what do you mean by large ensembles?
So large ensembles means that you train different models and then you average the results. So in this case, for example, this notebook I've used YOLO. You can also opt to use another model like faster RCNN, and then now use average the predictions from both YOLO and faster RCNN to improve the performance of the predictions. So we don't recommend that because it means it will take more time to run. And then during inference, it will take even more time when you are trying to make predictions because you have to make predictions on two different models. So that's why I discourage in samples.
Okay, that's good. Thank you. The last question that I see here, are there records of generative models being used for detection?
Um, I think so. I don't know whether SAM qualifies. There's the segment all model from Facebook or
Hmm.
from Meta. I think it's kind of generative. I don't think it's generative.
Hmm.
Yeah, I have no idea. Most generative AIs are for generative AI usually means you are generating something new.
Yeah.
So when it comes to detection, I don't think you are generating something new, but you are making a prediction on something that already exists. But
Yes, you could use the generative AI model to generate the models used in the challenge to make predictions.
yeah,
Maybe.
so maybe I can answer it this way.
Hmm.
You can use your generative models to create more training data samples. If you have the resources, you can use something like stable diffusion, create more images that have white blood cells, and train your model on a larger data set, which might improve the overall performance.
The next question is, can we get the recording starter notebook and other materials used here? Yes, of course. The starter notebook and other materials are all available on the Zindi challenge page. The recording we will upload to the challenge page. Well, we'll upload to YouTube and it will be available on the challenge page within the next few days. So that will be available. Um, the next question, explain more about the GPU. That's quite vague. Um, Mercy, maybe the question was from Mercy Wamanga. Maybe you could just rephrase that question so that we understand a bit more what you're asking and we'll try to answer it. The next question, in a nutshell, a single model is required, not using more than one model since ensemble of models is not allowed. Um, Let me just double check the wording of the page. Um, so we are saying that large ensembles are allowed but not encouraged. That is because these models are supposed to be applied at scale. Um, yeah, there we go. It's in the resource restrictions section. Just keep scrolling down. Yes, there. So we need the submission to run on a single GPU with less than 20 hours training and 2 hours inference. If you can create an ensemble solution that runs within that time, you're welcome to do so. There is a question about image augmentation and whether that can work. Maybe you can answer that briefly, and then I'll hand over to Rose.
Yes, it's encouraged that we use data augmentation. So usually I usually confuse data augmentation with increasing the data set, which is not the case. So data augmentation means that you increase the diversity of the data set. So what it means that, for example, if you look at this image, let's assume you're applying to gray data augmentation. So to gray, it means that it changes this image from a colored image, that's from 3 channels RGB to just 1. So the model will have to learn something new by just making predictions on just a single channel image. But remember, it's the same image. We haven't increased the data set, we just have diversified. So when you diversify the data set, your model will be able to generalize well. It will be able to make good predictions on unseen data set. So for YOLO, if you go to the YOLO page, our website, there are a couple of argumentations you can use. I don't know if I can take a quick look here. Yeah, there are quite a number of argumentations we can use. Let me try to see whether they are. Okay, this will take a bit of time, but yeah, you can do a bit of research there and you can see there are a bunch of them. And in this example notebook, we applied these ones. So some of them can improve the performance of your models. Some of them can deteriorate the performance of your models. So that's where you have to do hyperparameter tuning, try experiment. Like usually with these models, the main thing is experimentation. You create an hypothesis, try to prove that if that hypothesis is true or false. If it's true, then your model will improve. If it's false, you leave it and then move on to the other one. I think that's the simple answer I can give.
Thanks, Darius. There are a number of questions still coming, but we're coming up to the hour, so I'd like to give Rose a chance to talk a little bit more about the sourcing of the data set and how the data set was created. And then once that's done, we'll answer any other questions that may come up. Thanks very much, Darius. Rose, over to you.
Thank you very much. And I hope you're able to hear me now.
Yes, we can hear you.
That's great. Thanks to the previous presenters on the insights around the dataset that we've created. I think that's very impressive. And the learnings that he has been able to share with us. I think that's very good feedback to us. I'm Rose Nakasi, the principal investigator for the project Malaria Dataset, Lacuna Malaria Datasets. And I'm a lecturer at Makerere University, as well as the lead of the Makerere AI Health Lab. And I'll be talking about the dataset for AI-based detection of malaria. This dataset was funded by Lacuna, and I'm glad they are here with us to witness our milestones and how far the dataset can be leveraged for developing great diagnostic or detection models for malaria. I'm presenting on behalf of the team that developed this dataset. It was a team from Uganda and as well as a team from Ghana, Minor Health. And we've been doing this work in collaboration with the Makerere College of Health Sciences. And I'm glad that Dr. Alfred is here with us through the Mulago Referral Hospital, and as well as Chirudu Hospital from Uganda, and from Ghana, we're collaborating with Kolebo Teaching Hospital. About the work that we're doing at Makerere Lab is that we're leveraging the use of artificial intelligence to solve some of the pressing health challenges that we face in our context. And we are mindful about the health challenges, especially around diseases such as malaria, tuberculosis, cancers, and any other infectious diseases, but leveraging on the cutting edge technologies of artificial intelligence. And we're doing this collaboratively with the healthy practitioners in the different healthy facilities, but together with the Makerere College of Healthy Sciences. And our vision really is to be able to transform healthcare through innovative artificial intelligence solutions. Now back to the motivation for the data set and the impact of what it is able to provide in the long run is that from our context, we look at one of the most life-threatening disease, which is malaria, and it's caused by parasites. And it is one of the top 10 causes of death in the sub-Saharan Africa. And globally, we're looking at it statistically standing at around 3.4 billion people in more than 92 countries that are estimated to be at risk of the disease. So we really see a very big burden in terms of the public health concerns around malaria prevalence. In Uganda specifically, it has been attributed to account to over 27% of deaths. So locally speaking, it's also one of the most endemic diseases, not only globally, but also at country level. So looking at our motivation to be able to look at cutting edge technologies to be able to counter some of those health challenges is the motivation for this work, but also not forgetting that we have a few trained personnel like Dr. Alfred to be able to man the gold standard mechanism for diagnosis of malaria. So that means that in most of the healthy facilities, some of them go without even a trained technician to be able to man the gold standard mechanism for diagnosing malaria. Statistically, in Ghana, there was a study that was carried out and it attributed more microscopes to even the lab technicians in the hospitals by a ratio of 1.72 to 0.85 as a ratio of microscopes for the lab experts. And this was for a big population of over 100,000. So you really see that the skill set is very limited in most of the highly endemic settings. But also not forgetting when you look at the gold standard mechanism, which is by the use of the microscope, and according to the WHO guidelines that do not require a microscope is to be able to view more than 30 slides a day, based on the endemicity of diseases such as malaria. So that means that very many people are going to go either without a diagnosis or they have to make huge lines and queue up to wait for the microscopist. So some of them resort to methods such as treating by symptom or RDTs, which are sometimes limited, especially when malaria is at low parasitemia. It might miss out on detection of malaria. But also the mechanism of using the microscope, which is intuitively eye straining, and therefore the expert has to really strain out at the end of the day the eye to be able to view those very small pathogens, the microscope. And that means that very few people are going to go either without a diagnosis or they will actually be diagnosed wrongly. And that means they will either take medication that they are not supposed to take, which literally leads to cases of drug resistance, and in the long run, the high cases of mortality that we're witnessing. So as Makerere, we came up with this innovation of leveraging existing technologies such as the microscopes. At least in our setting, we have a microscope at every public healthy facility level, and also in the public healthy facilities, there are microscopes, but also the smartphone technology that is coming on board, where it is estimated that by 2030, almost everyone will be having a smartphone. So leveraging on that existing equipment, but also the cutting edge technologies such as artificial intelligence, that offer us capabilities for computer vision, as Darius has highlighted. We're able to come up with a solution. We believe that this is a solution that will be an ends to the means to proper diagnosis and detection of malaria. So the prototype that you're seeing in there is our setup, where we're hinging a smartphone onto the eyepiece of the microscope. And that is where the project name comes as ocular, because we're looking at the eyepiece and supporting the eyepiece capabilities by having a 3D printable adapter that we attach, that provides an attachment of the smartphone onto the eyepiece of the smartphone, so that we're able to capture whatever is under the microscope onto the screen of the smartphone. And this isn't the work of the experts without having to strain their eye, but also to allow capture of the image onto the phone. But also we can seamlessly be able to use the phone to do the analysis and give inferences of detection of malaria. So what of our interest is that image, and we characterize this. We've been in close collaboration with the team at the College of Health Sciences and in Mulago, who are characterizing for us the pathogens or the objects of interest in this end. We were looking at trophozoites, which are the malaria parasites, but also the white blood cells, which eventually will be able to support on quantifying parasitemia at the end of the day. And I think at an opportune time, Dr. Alfred will be able to give a highlight on part of that science. So what it was, the data gap that we sought to counter is that previously we had been having some of the use cases around malaria detection using artificial intelligence, but we weren't very cognizant about the environments under which these data sets were collected. So through this, we are able, one, to create an open source and well-curated image data set that is inclusive in terms of being aware of the different settings. So we had to take care of understanding the characteristics of the settings under which these images were curated. A point in case like taking note of what phone and what resolution comes out of it, but also taking into consideration aspects of the resolution, aspects of the type of microscope that was used while capturing the images, but also the different magnifications that were used while we were capturing these data sets. So we believe that this is a very rich and benchmarking data set that is well aware of the environment, because having a standardized environment or a standardized protocol for data collection is usually very good for generalization, but also a representative that you can be able to repeat it over and over again and consistently getting results. The whole idea is that we want to open source this data set so that we can be able to hear and get feedback from the different scientists around data. For example, the example that Darius has been presenting, researchers in machine learning, to be able to, come up with insights that all speak to coming up with models that can, support correct and more accurate diagnostic models for malaria. So the characteristics of the data set is that for this particular challenge is we open sourcing thick blood smear data sets that were collected from Uganda. And for the training, and I think this information is already in the call, 2,747 images in the training set, while 1,178 images in the test set. We believe that using this data set could provide us some baseline investigations that could spur more improvements in the future. So we're looking out and looking forward to many data scientists and machine learning experts to check out this data set and provide insights. And we thank Zindi for spearheading this initiative, for giving us an opportunity to bring on board very many different machine learning experts to provide insights on our data set. How the data set was developed, of course, we have been working in partnership with the medical facilities, specifically from Uganda, Mulago and Chirodu. And the idea is that we had to come up with a protocol, data collection protocol, which was aware of the different settings that I mentioned earlier. And so we had to also come up with data collection tools and training the experts at the hospitals because these are new tools to them. So they had to undergo the training of how they could be able to follow the standardized data collection protocol. And this was done again in collaboration with the team from the College of Health Sciences that was spearheaded by Dr. Alfred here with us. We also had to do data collection and validation at the end so that whatever was collected from the different microscopists had to go through a validation phase with the experts who are WHO certified experts to give us a good representation of the data that was collected. We also underwent a process of the annotation phase where again experts in the different healthy facilities were taken through our data annotation tools to be able to come up with the characterizations of the objects of interest. And in this case, again, I'll re-echo that this for this particular challenge, the trophozoites and the white blood cells. And this data is already publicized in an open access storage, which is at Dataverse. And that's why we're hosting this data set. So for the Lacuna malaria detection, and I know that the Zindi team has ably presented this, is that we want to be able to develop a multi-class detection task where we're able to characterize and detect objects of interest. And in this case, we are looking at both the trophozoites and the white blood cells. So we're looking at a team that will be able to give us correct identification models and classification models for this task. We are thankful to Lacuna Fund for continuously supporting our engagements in curation of localized data sets. And we believe that the bigger goal is to be able to come up with solutions that are able to counter some of the health pressing challenges in our context. Thank you very much.
Thank you so much, Rose. I'd love to hear a little bit more from you about how you envision the winning models from this challenge being put into practice now or in the future. Would you have a comment on that?
We hope to be able to engage, especially with the teams that are, of course, that will reach the satisfaction of Zindi out of this challenge, because the whole idea is to have a collaborative, team where we're able to advance research around malaria detection. So that is one of the aspects, and probably these insights will, again, collaboratively with the teams, we need to publicize them probably in a research journal, where we able to then share the insights of the challenge to the general public.
Thank you so much. I think that's really exciting for some of the people working on this challenge to be able to collaborate with the research team and really see an impact of the solutions that they build. So it's really great. Okay, so I'm just looking at the chat. I see one question about access to the slides. Rose, I'm sure you'd be willing to make the slides available after this call. Is that correct?
Yeah, I'll be able to share with you.
Yeah, maybe supply them to me and I can share them with the attendees. That would be wonderful. We will also be sharing the recording of this webinar on our YouTube channel and on the Zindi Challenge page, so you'll be able to still see all of this information.
Okay.
Okay, so I'm looking through some of the other chats. Thank you so much, Rose. I'm looking to see if there are other questions for you or possibly questions still for Darius. I see. Okay, so the last question was how was the data set collected? I think you've touched on that really in depth. I don't think that needs to be answered any further. Um, right, a question, can we get some insight around the allowance of external pre-trained models or data set? I see there's a conversation going on in the chat. Let me just make Zindi's position very clear. I'll take myself off mute so you can see me. So yes, so the default position when it comes to data sets is that the data sets that you use for your for the challenge, for building the model to compete in a challenge, should be only the data set provided as part of the challenge. So we've worked really closely with Rose and her team to identify the correct data for this challenge and make that available for you. In some cases, there is open source data that may be useful to the challenge without representing any form of a data leak or without breaking the competition in any way. We are always open to considering the use of this data, but that does need to be brought to the Zindi team so that we can review it and then make that information available to all participants. So we won't allow you to just go out, find your own supplementary data and use it. That will result in a disqualification of the solution. But if you find something that is open source and it is useful for the challenge and it doesn't end up causing a leakage, we would encourage you to bring it to us so that we can review it and then hopefully share it with all of the participants. This is different. The difference that should be noted is between open data and open models. You are encouraged and welcome to use pre-trained models in this circumstance, but not open data sets outside of the data provided for the challenge. Right. Another question, are we allowed to use other data sets? I think I've answered that. I see there's another question for you, Rose. Do you anticipate the data and models may be used by the hospitals you're working with for detection in future?
Thank you for that question. And I think that's the bigger goal. And I think that's the reason why hearing some perspectives from our collaborators from the health background could give a very good sense of the impact the datasets are creating are for, and how actually this will, in the long run, be able to support the work that they are doing. So if you may, I don't know if at an opportune time you'll be able to call up Dr. Alfred to give some remarks on this.
Yes, Dr. Alfred, if you're available, you're most welcome to come off mute and share some insights with us.
Yeah, thank you so much, Zindi Rose, for the presentation. Yeah, so from the health perspective, I think this is a solution that has been overdue. The challenges that Rose presented are typical, and these are not only here in Uganda, across most parts of sub-Saharan Africa, and probably where malaria might be endemic and the human resource is limited. So when we heard about this and we were able to share with the Ghana Ministry of Health, and especially where the malaria control program sits, they were quite excited about it. And there were questions they raised not really about whether the technology will work, and it's more about how it will work and whether it will be feasible to deploy at an affordable cost. So they were looking at those, and they were able to allay their fears that this may not work, because we know from a survey that we did recently that most of the few lab techs that it was mentioned still have smartphones to adopt this model. And when we moved around the country, everyone was excited to employ this, such that it will be able to relieve them time to attend to other diagnostic demands. And so in terms of whether this will have an impact, I must say certainly that huge impact that the public is expecting. And the politicians, for us here, you have a layer of different stakeholders to approach, starting from the immediate users, the clinicians, who are primary users of this platform. Then the Ministry of Health through the Malaria Control Program, who are eagerly looking into this to come and try to allay, and reduce the fight, reduce on the malarial resistance, which is rampant. Because there's a lot of mistreatment of fever here, and it's a huge challenge. So I think the future is bright. All the small things that are being done to improve it, making this data set available to the scientific community, I think is a huge contribution. And we eagerly look forward to a product that's deployable in the health up to the community level. Thank you.
Dr. Alfred, this is really a wonderful insight and perspective that you shared. And I find it very inspiring to hear that the solutions from this challenge will be welcomed by the communities that really need them. I think that's wonderful. So I'm looking through the remaining questions. I see there's a question about sweeps that Darius has already answered in the chat. I've answered the question about where the competition page, where on the competition page you can find the starter notebook, and we've answered the questions about the data set. Okay, it looks to me as if there are no further questions. I'll happily allow a chance for anyone else to ask anything else now. We are over time on this webinar, but generally speaking, we make ourselves available for as long as we need to answer all of the questions. Yeah, while we wait, let me share the page for everybody. So in case you haven't seen the challenge page, I'm sharing the link to the challenge page there in the chat. And I see one other question. Is the specific objective to identify all objects in the smears or to identify only the malaria infected ones? So that can be seen on the challenge page. And here we state that the objective of the challenge is to develop a multi-class object detection and classification model that can correctly identify and classify malaria parasites in blood slide images. If you want to look in more detail, you can look at the evaluation page, and you can also look at the data page. I would also suggest that you take a look at the sample submission file, you look at the starter notebook, and so on. Darius, do you want to add anything to that answer?
I think you have answered it. So the objective is to make predictions or try to find the bounding boxes for just two parasites. I don't know what they are parasites, but you are supposed to just make predictions whether those small smears are trophocyte or white blood cells. That's the main focus. Yeah.
So that would be two classes. You need to be able to predict the trophozoite and also predict uninfected blood cells.
Yep.
Fantastic. Thank you for that answer. I think that then brings us to the end of this webinar. I'd like to extend my thanks to Jennifer, to Rose, to Alfred, and to Darius for being here and sharing your experience and your expertise. I'd also like to say thank you to all of the participants for your interest and your passion in this challenge. You have 2 months left to work on this challenge. The challenge closes on the 17th of November. So I hope that you will use that time wisely to research the challenge or the problem in depth, understand exactly what the challenge is about, and then really put a lot of time and energy towards building the best model that you can. I would encourage you to read the rules very carefully if anything isn't clear. We will, of course, be available to answer any questions on the discussion board if you do have them. So with that, I'll wish you all a very good evening and thank you for being here.